Welcome to the introduction for Module 3 and 4 of the Year 11 IS course. And what we are going to do today is just very quickly go through some ideas to what scientific models are. And of course, this first little one here, what we are talking about here is models that inform understanding. And that's a really important concept. Scientific models' job is to help you understand a concept. And of course, that's our definition there. A model, anything that understands to make a concept easier or, just to understand it. Now, of course, in some cases some models and sometimes scientific ideas are very complex. And the model makes it easier to understand something. And you've been exposed to scientific models ever since you started studying science. The example we use a lot, and we'll see it here later on, is atomic theory. And we start off, atoms aren't little spheres, but that's an important place to start off with. It makes it easier. It's very hard to start understanding the atom if you started learning quantum mechanics and quantum interactions or quarks and all that before you understood the basics. And so one of the things there, most of the time, and it's really important to understand that a model just looks at one part, okay? Just one part of that there. And just by looking at one part of the overall concept, it makes it easier for you to understand. Over time, you might use several different models to build up your understanding. And as you achieve that understanding, you can get more complex. Another example that we'll see here is that when you introduce cells, you don't talk about the actual really intense really microscopic view of the cells because there's a lot going on in there. You usually start off saying, well, cells, what builds up living things, it's got a membrane, it's got some cytoplasm, it's got a nucleus. And you say, well, that's your basic animal cell. There's a lot more going on. But what you're doing is just building the understanding. And once someone understands that bit, you then say, well, okay, in the cytoplasm, there's a bit more. And of course, history of science is basically about new models being developed. You can often talk about the fact that these models are also linked to technology. And some of the times, particularly when it comes to very small and very large things, it's very hard to understand something without actually having the technology that allows you to explore that. And as I said before, the atom is the main one that we're going to look at here. And the idea of developing models is how we go on there. Now, when you look at the standard sort of thing here, ancient Greece is normally where we start the story. There were, however, at the same time, there were scientists and philosophers in China, India, and places in the Eastern world who were doing similar things. It's just that obviously most of what we accept as scientific now, we go sort of almost start at the ancient Greeks, although other people had some interesting ideas as well there. So of course, this is all goes back to Democritus. And the reason we do start at Democritus as well is because the word atom actually comes from an ancient Greek word, atomos, uncut, divisible, ancient Greece. And one of the things there, he did come from this from a philosophical point of view. And I think the analogy they use is you take a piece of cheese, you cut that piece of cheese in half, then you keep cutting in half. And eventually the thought experiment is that eventually would you reach a point where there is nothing else to cut or you can't cut any further? And of course, this is one of the things that the ancient Greeks were very good at coming up with these ideas. There was no way to prove it or disprove it at the time. And it actually took 2,000 years for this to actually develop a little bit further, which comes to 1803, John Dalton. And John Dalton, he was a chemist, and one of the things he was doing is he was looking at the way oxygen and hydrogen interact. And so he did a whole heap of experiments and said that every time he took a bit of water, or he took an amount of oxygen and an amount of hydrogen, reacted them, they came up with an amount of water. And it was always in the same ratio. 1 bit of oxygen to 2 parts hydrogen gives you 1 bit of water. And he came up with this idea that, well, for this to happen, maybe all matter needs to be in small particles. And so he revisited the idea. He took the name from ancient Greece, and we get the start of our modern view of atoms. And then in the 1800s later on, we're able to, or scientists, engineers, clever people, were able to develop new technologies. And this one here is the cathode ray tube. Essentially, it's a glass tube that's been made into a vacuum. And it was only in the 1800s that these could be developed. One, it was the discovery of electricity and the ability to make high voltages, and the fact that glass making by this time could actually be really precise and really. So what you need to get the cathode ray tube is you need a very uniform piece glass tube that's completely sealed. And by doing that, passing all this electricity through it, they found these weird green rays coming out. Now, of course, they eventually became, well, not modern, but old TVs, the first televisions, which used cathode ray tubes to shoot electrons at a fluorescent screen. In this case here, Dalton's ideas, while they could be proven by experiment, they could be further confirmed by the development of a technology. The ancient Greeks would never have been able to do this because they didn't have the technology to make the cathode ray tubes. Now, this idea eventually led to J.J. Thomson coming out with this thing called the plum pudding model. The best analogy we can use now, because plum puddings really, particularly in Australia, are not that big a thing, is I usually like to say it's like the blueberry muffin or the choc chip muffin, where Thomson's idea was that the cathode ray tubes had shown that there were these little negative particles here coming out. And, according to what they're saying there, well, if there's negative stuff coming out, for there to be negative stuff, there needs to be positive stuff. And so he said, well, maybe the atoms, because it was only the electrons being ejected, they couldn't see anything else other than the electrons being ejected. Maybe these little electrons here were embedded in this blobby positive stuff. And this blobby positive stuff, with enough electricity, would eject the electrons and shoot them to the other end of the cathode ray tube. Now, again, it's an idea that's supported by some of the evidence there. Then we go to the early 20th century, and Ernest Rutherford and his two students, Geiger and Marsden, conducted this experiment. Now, this is a really interesting experiment. One, this needed another discovery. It actually needed the discovery of radioactive materials, because what we have here is a radioactive source that's firing off alpha particles. Now, the alpha particles were known to be, by this time, they were quite heavy. And what they thought was that these alpha particles were pretty heavy, and if the atom was made of blobby stuff, what would happen would be these alpha particles would either go all the way through or be blocked by the blobby things. But they found something completely different. Most of the particles went all the way through. They were not deflected. There was nothing going on there. Some were deflected at angles, and some, very occasionally, and I think it was about 1 in 10,000, were pushed all the way back out. They couldn't be detected. And so Rutherford came up with the idea of saying, well, if most of the particles are going through to the end, a small amount are being deflected, and some are being deflected right back, this means that the structure of the atom must be a little bit more complex. And so he came up with this idea that atoms were mostly empty space, but had a very dense nucleus. And the dense nucleus is what was deflecting things all the way back, or deflecting it to the side. And again, this is our almost modern view here. The atom's a dense nucleus. There's protons and neutrons with electrons orbiting. The analogy here, which is like that little animation there, and this is one that's still used today because it helps build your understanding, is that an atom is almost like a mini solar system. The nucleus has most of the mass, it's quite dense, And that's similar to what happens in our solar system. Most of the mass, nearly all the mass in the solar system is in the sun, and the planets have a little bit in they orbit around. Now, one of the problems there is that, and even people like Rutherford and that knew it at the time, is that what we're saying is that this nucleus here, most of the mass is there, but it's positive. The electrons around here are negative. And so while this serves as a reasonable analogy, it can't be the true nature of what's going on, because otherwise the electrons would just go in there and everything in the universe, in the atom, would disappear in an instant. It just annihilate itself. Now, there was a lot of clever science goes on there, and we're not going to go into a whole heap of this here, because once you get past Rutherford, which is, I think it was in the 1910s, things accelerated greatly. People like Chadwick discovered the neutron, and then we had a whole heap of other people, de Broglie, Bohr, Schrodinger, and that. And they all eventually developed this idea that atoms are weird. Subatomic particles, things that we know make up matter, also act like waves at this what's called the quantum level. At the incredibly small scales, things are incredibly weird. Now, this is the thing. You can't, if you think about this in terms of models, we can't get to this weirdness without having an understanding of the other stuff there. And so in that way, even though the solar system model of the atom is wrong, it's a good stepping stone to actually understanding more of what's going on. And this is probably reasonably close to what we think atoms actually are at the moment. They're very wavy, and that the matter is a lot weirder. We don't notice it at our level because we have, the bigger something gets, the less wave-like it is. As I said before, each step, it's just a snapshot to explain what's going on. But they're all models. And they're all models that we're building up. One of the key things in science is even when a model is accepted, or an idea or a theory or a law is accepted, there is still room for improvement. That's the one major difference between science and theology or belief or anything like that, is that science will always accept that there can be something wrong. A scientific concept is one that can be proven wrong, but then you prove it wrong and you get something better out of that. Now, there are 5 main types of models that we are going to look at. Now, the first one here, diagrams, pretty easy. You've done that ever since you've started science. Books in particular have plenty of diagrams. You may have also played in class with physical replicas. One that you often use in junior science is something like a wave machine, which shows you how waves move. This can also be something as simple as if you're trying to understand waves, playing with a skipping rope, and you can actually see that there. The third one, mathematical representations. That's essentially just a fancy way of saying formulas. Formulas are types of scientific models that explain something, and we'll look at that in a little bit more detail there. Analogies. Now, analogies are an interesting one, and you will have been exposed to these a few times, particularly when we are doing stuff, electricity. When we introduce the concepts such as scientific electrical circuits, we often start talking about that a circuit is a little bit like a water pump, and we'll look at that a little bit more. Now, computer simulations are ones that you may have mucked around a little bit with, but probably not necessarily in a huge amount of detail. But they're a fancy way and a really effective way of understanding a scientific concept. Climate change is based on computer simulations. You can play with computer simulations to do virtual experiments and a whole heap of things like that. As I said before, diagrams are the most familiar concept. They're simply showing a picture, a poster, a book diagram, any sort of image that you look at, which helps you understand the process. So if we have a look here, this is similar to what I mentioned before. This is a simple cell diagram. This is usually how we introduce cells. We say a cell is this thing here. It's got a nucleus, which controls everything. It's got cell membrane, which holds everything in. And it's got cytoplasm, which is all the stuff in there. That's how we introduce the topic. It's not the entire picture, by no means, no stretch of the imagination. It is simply trying to explain to you what the concept is. And once you understand that, we then go to something here, which is a little bit more complex. Although really it's not as complex as what cells actually are sometimes. And of course, if you look here, this is pretty much that same diagram with more stuff in here. Things like Golgi apparatus, mitochondria. You need mitochondria to power ribosomes, lysomes. And of course, my favorite ever cell words, smooth endoplasmic reticulum and rough endoplasmic reticulum. The names that sound a little bit funny, but what you're doing is you're going to the next bit there and saying in the cytoplasm, things like mitochondria, which give cells their energy. You might also talk about plant cells where you have things like vacuoles, which store chemicals and things like that. And you can even then get in a little bit further. And this one here, which goes even further. And of course, one of the things here you also notice that as diagrams get more complex, they often get a little bit more scientific in their words here. So, nucleoplasm, cytosol, endocytosis, exocytosis. Now, if this was your first introduction to cells, most people, including myself, would freak out. It's like, I can never understand this. That's what you do with models, is you start simple and you build up the understanding. And as we just said there, and as you get more, it's more complex, but it's also a lot more of the meta language comes in there, a lot of the scientific language. And the reason scientific languages were used is because the use of a scientific term has a lot of other things that go with it. So if you use the word combustion, you're saying, well, I'm burning something in the presence of oxygen. One word can actually imply a whole other level of meaning. Now, physical replicas. Physical replicas take something and they try and show how it works. Now, this one here, example, is a little solar system model, which is quite common. And what you do is that by that spinning around, you can actually model the motion of the planets. Now, if you look at this one here, this is a fairly simple one. And of course, it just gives you the idea of the concept. It doesn't show you the relative size of the planets, doesn't show you the relative distance between the planets, because that would add another layer of complexity, which will do it. But it starts giving people an understanding of how these models work or how these phenomenons work. And of course, here you can see here, this is a slightly more complex version of that there. It's the same basic concept. It's just mechanical, so it can go around there. And this one's also added another layer of complexity, which is showing the moon going around the Earth. And what this also allows you, some models allow you to manipulate it. So you say, well, what's going to happen if I do this? If I move this section here, if I move that? It allows you to do that and actually build in your own brain a bit more understanding. Mathematical representations. Now, these ones here, usually in physics and chemistry, usually has the most mathematical models, but they are also very common in bio and earth science as well. Particularly when it comes to earth science, when we're talking about climate modeling and things like that there. So one of the easiest ones is just Newton's second law, F is equal to ma. And so essentially here, and you can rearrange it, but the amount of force that you have to apply on an object to accelerate it depends on its mass. And so in this one here, we've got F is equal to the force, m is the mass, a is the acceleration. And that's relatively easy. Most people can easily manipulate a three-part equation. It's quite easy to do. Now, of course, this one here, we're dipping into analogy here, but you've got two examples. You've got the truck there, and as the truck is broken down, and we've got a little clown car down here. Now, what we are assuming here, that clown car if you learnt anything from TV and movies, there's probably about 50 clowns in there. So that's a lot of mass. We're assuming there's no clowns in the car. But which one is easiest to move? And this is where the formula can help us here. Your intuitive thing would be say, well, it's easier to move the car. Newton's second law actually gives you an explanation, gives you a way to back up your intuition. So if we have a look here, the truck, let's assume the truck has a mass of 10,000 kilograms. We rearrange the formula to make A the subject so we can work out the acceleration. And if we're applying a 100 Newton force on that 10,000 kilogram mass, we get an acceleration of 0.01 meters per second per second. Okay, that is relatively pretty low. If you keep on pushing, you'll eventually move it. But we look at our car, and our little clown car, minus the 50 clowns, is about 1,000 kilograms. Do the exact same thing here, and we can say, well, okay, we're getting a bigger acceleration. Now, one of the things there, if you've ever seen someone move a car like that, it takes a little bit of effort in the start, and once it's rolling, it goes. And as we said before, this mathematical model confirms our common sense. And that's the beauty of using these models. Now, of course, yeah, we also know by usually Russian car cams that you can actually quite easily see that anyway. Now, analogies. Analogies are a really important thing in science, and you may have used them, you may not have used them, or you've probably used them without even thinking about it. And the common one I talked about before was this water pipes. So what we have here, and this is the thing here, we're saying electricity is like a water hose. You have voltage in an electrical circuit, and voltage is the pressure pushing it through. So we often say that, well, it's just the force, and voltage is a force pushing the electrons through. Currents is like the size of the hose. This isn't the best one here. We'd probably usually say current is the amount of water going through, which is dictated by the size of the hose. And resistance, you might have sand or something in there. So again, one of the things here, analogies, not necessarily always correct, but they're about building the knowledge. And then you can come back later on and say that there. And so, this is the one thing, so here, this diagram shows it here. So the voltage is from the pump or from the pressure, goes around there. The electrical current flow is the water going through here. Now, if you've got sand or anything in there, that can be a resistance to it. And then we apply that directly to what's over here. Our battery is like our pump. Our current is like our water flowing through. And our sand is a little bit like the light bulb. Then you can further refine that and say, well, we need to do it as a circuit diagram. And we can show that there. Although most of the diagrams that we do, we don't actually usually show I in that way. Now, the last one here is computer simulations. Now, these are the newest ones. Computing really has only developed in the last 50 years. And personal computing, personal computing is something that's only happened in the last 30 years. Of course, everyone now has their own computer. Now, of course, you do need to be careful that things don't break. Now, one of the ways that this has been used really effectively is in earth science. So here we've got an obvious computer simulation of tectonic movement. And this is sort of it's going backwards, showing how we had continents moving and the fact that the southern continents were part of Gondwana, the northern continents were part of Laurasia, and then we go further back to Pangaea if you want them all together. But this is easy to do because you feed the information into the computer and the computer runs these over really quickly. Now this one here is another computer simulation, obviously in earth science, where they're looking at current climate trends and looking at snow in the North American, so Canada and the United States. And the fact that, snow, according to these predictions, is going to be less and less over time. And, it's the idea that the Americans want their white Christmas every year. Now, one of the things there, all these models, particularly the climate models, they need to be adjusted. as new data becomes available. And that's one of the things that's been criticisms of climate models in the past. That people who are trying to deny climate change will say, oh, yeah, but your model didn't account for this. And that's the thing. Climate is so complex that you need to adjust things all the time. People discover new things, like there's new ocean currents and that new vortexes in the atmosphere and things like that. You can never always predict exactly what's going on. And science is self adjusting like that. New data becomes available, you change the model.